Good morning, everybody. I'll start with some basic things about regular local rings. And if you remember, I was talking about this flatness and fiber conditions. So if I'll just quickly take you there. Yeah. So this is what we were discussing in the previous lecture. And I said that the conditions on R and R dash, where R and R dash are Noetherian local rings, and condition on this fiber ring. This is how it is defined, right? So let me highlight, yeah, this F. And then how the properties can be read through properties of R, R dash, and properties of F. So that was the main topic that we were discussing. And I kept this theorem as E stroke T, and that means it's to be discussed during the tutorial or to be taken as an exercise, and Joydeep has already planned that, and he will be doing it after my lecture. And if you remember that this was the theorem that we were about to discuss. So if Rn, R dash, and F are as above, so Noetherian local rings with local homomorphism, and F is the fiber ring, then if R is a regular local ring and R dash is Cohen-Macaulay, okay, and if you have this dimension equality, then you have the flatness. So this is something very, very important, that under what kind of conditions on R, R dash, and on the fiber ring you have the flatness. So I said that we will do it, but after I introduce regular local rings, some elementary facts, and then we will come back to this. Okay, so this back and forth movement will happen because there are lots and lots of results, and some of these will be discussed in the tutorials or put up as an exercise. Okay, so this is what I plan to do today. So let me start. And there is certain portions, some elementary things which I will just recall, but that you have learned in detail through Professor Patil's lecture and also through Professor JKV's lecture. So a bit of an overlap. It's not really an overlap. I'll just quickly pass through. Okay, so as usual, this denotes a Noetherian local ring, and M is a finitely generated R module. So you know that this makes sense. So mu M, this denotes the cardinality of a minimal generating set, a well-defined notion. And this is given by this dimension of this vector space over this K. K is the field R model, right? Okay. So the embedding dimension is defined to be this number, this mu M. Okay, and let us write this M dim of R for the embedding dimension, the shorthand. Okay. And now here comes the definition that a Noetherian local ring is called a regular local ring if the Krull dimension matches with the embedding dimension. By the way, do we have any, if the equality does not happen, do we have any kind of inequality here, or? Between dimension of R and embedding dimension?
Dimension of R is less than equal to embedding dimension.
Okay. So equality is the definition for a regular local ring. Okay. And this is, I have put it under E stroke T. You can see it immediately that if you have a zero-dimensional Noetherian local ring, then R is regular if and only if R is a field. Anybody who can take an attempt and answer this? What does dimension 0 mean?
Maximal ideal is 0.
So
R becomes a field.
And the converse?
R is field, then it's obvious.
Okay. So this is something very, very trivial, but dimension 1 case is the interesting one. So we will see the discrete valuation ring occurs when you have the dimension 1 case, but we need a little bit of preparation before doing this. Okay, so now this is the preparatory stuff. That's what exactly I was talking about. And this you have already learned. I know that through, you have heard it a number of times, but still I thought, and my principal reference for these two things, for flatness, it's mostly Matsumura's book, and for regular local rings, I'm using Professor Balwant Singh's book. So I wanted to make sure that the notation, etc., are also at par with, because you know, otherwise that creates confusion. Okay, so this ideal of definition and system of parameters quick recapitulation. Noetherian ring, suppose we will eventually specialize to Noetherian local. And A is an ideal such that you have this length is finite. Okay, suppose M is a finitely generated R module, then this is what I have put under E stroke T, that you can prove that if you have this, this condition, then you can show that for a finitely generated R module, you also have this for every n greater than or equal to 0. So the length of all these modules m mod a raised to an m is always finite. So this again is an E stroke T, you know by now what it means. You will try to do it. Otherwise, we will definitely discuss this during the tutorial. Otherwise, always treat these as exercises. These are the gaps which have to be filled in, but simple ones. Okay. Okay. So now we take the Noetherian local ring, and suppose I start with an imprimary ideal. Then you know what it means. Okay. And you have this. Are you sure about this fact? Are you sure about this fact? So if you have an imprimary ideal, then you have definitely this length is finite.
Yes, support consists of only.
Sorry, Jibar Singh is not very clearly audible. Say it again.
Support consists of only. Support consists of only.
Yeah, right, exactly. Okay, so anyway, I'm assuming that you have seen this. I'm sure you have seen this. So, but this is very, very important. Okay, we will be playing around with this imprimary ideal all the time. Okay, so therefore one can define this numerical function, which is also called the Hilbert-Samuel function. This is what the notation is. That is for an imprimary ideal Q. M is a finitely generated module. Okay. Now, if M is non-zero, then degree, Professor Patil has done it in detail, in very, very great detail, in fact, that we define the degree to be the degree of this numerical function, which is well defined because you know that if you have this two ideals A and B such that lengths are finite, and if their radicals agree, then you can prove that these two functions agree. So therefore, which ideal you are actually working with doesn't really matter. It's a well-defined notion. This is how you define the degree. And what Professor Patil has already proved.
Indranath,
yes.
the statement about the function.
Should I go back to previous slide?
Yeah.
Yeah.
It is only about the degrees are equal, not the functions are not equal.
Yeah, the degrees are equal. Of course, yeah, of course. Yeah, I actually should have.
So, if I may interrupt,
yes, sir.
This deg M you have written there.
Yes.
That I called it DM.
DM, absolutely. So
and the leading coefficient I called it degree. Leading coefficient times.
Yeah, so that is exactly what was the purpose behind it. So you know, every book has their own notations. So yes, you called it DM, correct. So anyway, you more or less understand. I mean, what I will be just sort of cursorily using it, and as Professor Jacobi said, that's the degrees match. So that is what we need to keep in mind. But what I want exactly, I'll come to that in a minute. Yeah, maybe I'll make it at par with Professor Patil's lecture notes. Yeah. So what we have, yeah. So a quick lemma, once again, I have put it under E stroke T, that for a non-zero module M and proper ideal A, you have this following statements are equivalent. This, you know, you can prove it using the support. It's it's quite easy actually. So let us take it as an exercise stroke tutorial problem. Okay. Now, again, I'm completely following Professor Balwant Singh's notation, by the way. Okay. So for a non-zero module M, the proper ideal A satisfying any one of these equivalent conditions, means either one or two. Okay. Then this ideal is called an ideal of definition for M. So what it means is that an ideal A such that this length is finite. Okay, which is equivalent to saying that this ideal is imprimary. Okay, so this is the definition of ideal of definition, and note that every imprimary ideal, in particular M itself, is an ideal of definition that we know. We have already discussed this. Okay, and here comes another definition. So for a non-zero module, Sm denotes the least non-negative integer S such that there exists an ideal of definition of M generated by S elements. So if you remember, these were defined. So in Professor Patil's lecture, so but there may be a few differences in notations, but otherwise you more or less understand what is. So what is very important is that if you start with a Noetherian local ring, then you have your maximal ideal, and you definitely know that this length condition is satisfied, and therefore you definitely know that you have this M primary, this ideal of definition for every finitely generated module M. Or you can start with any M primary ideal. Okay, so we will see how this is being used. So let me quickly pass through. Here it is. So this, you know that how dimension is defined through this supremum of these chains in the support. And then you have this. This is what I was talking about, that it has been done in utmost generality in detail, that if you have a Noetherian local ring and finitely generated R module, then you have this equality. Okay. And again, well-known definition that you have a sequence of elements in N, and it is called system of parameters for a non-zero R module M if your D is the dimension, this D, and this is an ideal of definition for M. You know what ideal of definition means, okay? So that means that the length condition is satisfied, okay? And a quick corollary is this, that if you have R elements in M, then you always have this dimension inequality. And you know, you have seen already in definitely, and Professor JKV has done so many very, very useful results and exercises especially. You have seen that these kind of things actually help you reduce it to a lower case, right? So that is exactly what will be done. Like if you can choose a system of parameters and then go modulo it, you kind of get into an inductive procedure, okay? And equality holds if and only if this can be completed to a system of parameters of it. So these are kind of the main things that I need. And another quick corollary is the following, that if you start with an element in M, then you have this inequality. So you're going modulo just this submodule generated by this, and then the submodule M, I mean, okay. And if A is a non-zero divisor, then the equality holds. In particular, every non-zero divisor belonging to M can be completed to a system of parameters. So these are the main things that I would require to prove that flatness, and under a, if you have local homomorphism of Noetherian local rings and the fiber, so conditions on that. Okay, sorry. Okay, now yeah, so coming back to regular local rings. So this is the first proposition, and after a while I'll go back to flatness. Okay, so you have a regular local ring, you know what it means. The total dimension of R is equal to the embedding dimension. It's of dimension D. And then for elements T1, T2, TR in M, these following conditions are equivalent. That this is a part of a regular system of parameters. You know what it means. That means this is in M and it is a system of parameters. Okay, so, and this is a regular local ring of dimension D minus R. So it was expected something similar, that you are dropping the dimension of the ring, and you will see that this is what will be used everywhere. And we will be mostly using the inductive procedure for proving this various results regarding flatness and other things. Okay. Okay, so this is kind of easy to guess, not very hard. So let me always denote by bar this quotient. Okay, and by the way, I am using this notation for the ideal, because sometimes it is better to avoid confusions. So let me use this notation. So this bar will always means this quotient ring. Okay, whenever I go modulo something. Okay, you have this, right? because R is of dimension D and this is a part of a regular system of parameters. So first of all, this is just a bunch of elements in M. So suppose we are proving 1 implies 2. So you know that this can be completed, this regular system of parameters, you complete it to a system of parameters, okay? And M bar, obviously M bar means the image here, so I mean the M mod this, is generated by this, okay? Because these are in M, and therefore you have this inequality, right? So dimension of R bar is less than or equal to that embedding dimension that you know, and then this is less than or equal to D minus R, the obvious reasons, okay? Because here you have these elements, and this is less than or equal to dimension R bar, and therefore you have the equality, and therefore you have proof 2. So 2 means this is a regular local ring of dimension D minus. Okay, and for 2 implies 1. So if you assume that this R bar, the regular local ring condition on R bar, then you want to show that this is a part of a regular system of parameters. Okay, so this is how you go about it. So the assumption this regular local ring of dimension D minus R implies that M bar is generated by D minus R elements, right? That is the definition, and therefore these are the elements if we assume, okay, with U1, U2, UD minus 1 bar in M, then it follows that M is generated by this. Is that clear to all of you? That if you know that M bar is generated by these elements, then when you sort of unquotient it, if I may call it that way, then these generate your M. Is this clear? Okay. Please speak.
Yes, it's clear.
Okay. Now look at this corollary, and once again, if somebody can answer. So R is a regular local ring of dimension D, and T is a non-zero element in M. Then T is not in M square, if and only if. This will be a kind of a, it looks like a very technical statement, but you will see it's extremely useful. Okay, if and only if this R mod RT, so the module of the principal ideal, is a regular local ring of dimension D minus 1. Can someone answer? So which part is sort of easier? So you can, the initiation is here, so you can guess what we will be trying to do. You have a non-zero element. Suppose T does not belong to M square groups. Suppose T does not belong to M square, so you have a non-zero element here, T bar, and then you, as a vector space element, you can extend it to a basis, right? So anyway, let me just quickly show you. It's not something very technical or anything. So kind of a, once you see this for a number of times, you see there's a kind of a routine argument. So if you have this, then it's non-zero, and therefore you complete it to a K basis. And that is if and only if T can be completed to a minimal generating set of M. This we know, right? So therefore T can be completed to a regular system of parameters of R. That's exactly what we need. And therefore it's a regular of dimension D minus 1. So it's kind of same argument that you are doing it previously what you have done seen for a system of parameters that you have this dimension inequality, you have whether you can complete it to a system of parameters and things like that. Here you have seen that if you have a non-zero divisor, then it can be completed to a system of parameters, etc. Now we are specializing. We have this M to be the nothing but the maximal ideal of the local ring, and therefore kind of similar arguments go through. Okay, so it's not if you kind of work it out, you will understand it immediately. So this proves this proposition and this corollary that if you have an element T non-zero, and T not in M square if and only if this is a regular local ring of dimension D minus 1. You can guess how it is going to be used. That the moment you have one such element, you can drop down the dimension, keeping the regular local ring condition intact, and therefore you can get into a kind of inductive procedure. So that's the whole idea. So let us see how we use this. Okay, so now comes a very important, well, we can call it a kind of a structure theorem, that every regular local ring is an integral domain. So here you will see a beautiful sample that how we keep using the induction. Okay, so induction is on the dimension of the ring. So first of all, D equal to 0, that you know already, that you have field condition and therefore nothing more to do. Now let D be greater than or equal to 1. Okay. So that means that M is not a minimal prime ideal of R, right? Obviously, because if dimension is at least 1. Now suppose this is the bunch of minimal primes of R. Okay. So therefore, please remember the notation. I'm not opening two ways, but if you want, I can open two windows. Okay, please let me know. Okay, so if this is the set of minimal primes, then you have this for every I, right? Because M is not a minimal prime. And this is also, this containment is also not possible, because otherwise you will have the equality and Nakayama will be applied, right? So therefore you have this. Okay, by the prime avoidance, I'm assuming that you know this prime avoidance. You just need that you have all these are prime ideals, so you can dispense this. That's not a problem. Okay, so therefore it's the generalized version, and therefore you have M is not contained in this. So you can choose a T such that T is not in the union. Okay, and therefore you are done. T is not in M square, and therefore by this previous corollary, it's a regular local ring and dimension is dropped by 1. Okay, so therefore you have an integral domain. I told you, right? It's the inductive procedure, right? Every time you will see it keeps coming back. This is the standard way of doing it. So you have an integral domain by the induction hypothesis. Therefore, this is a prime ideal of R. Okay, and moreover, height is less than or equal to 1. Fine. Okay, so by the choice of T, the ideal is not contained in any minimal prime ideal of R. Is that clear? Just to make sure that you are awake. Is that clear?
Yes, sir.
Why? Why?
Because we started with T belongs to M,
Of the choice.
but T is not in P1, P2, PR, and M square.
Fine. Because of the choice of T. Yeah. Okay. So therefore, I have height of T equal to 1. Again, somebody please respond. Why? So previously you had less than or equal to. You were ruling out the other possibility, and therefore it must be 1. Please respond.
Because it is avoiding all the
Sorry? Because
it is avoiding all the minimal prime ideals.
correct, exactly. Okay. So therefore, we may now assume that P1, let us take the first one itself, upward enemy. So P1 is not contained in RT. Okay. So if you take any element in P1, then obviously this belongs to RT and it's BT, and therefore BT belongs to P1. And we get B belongs to P1 since T is not in P1, and therefore P1 is TP1. Okay, but then T, you remember where is T? Where was T from? Where was T from?
It was from Jacobson article.
Exactly. So you have this, and again Nakayama applies. Okay, so therefore you have 0. Okay, so all these elementary things getting used in bits and pieces, and beautifully it comes to this fact. And P1 is 0, and therefore you have 0 is a prime ideal, therefore you have integral. So this is like, and you will see that this kind of argument that going modulo a suitable element, okay, always is the kind of technique which will be used, okay? And then some dimension inequality, and then some of these things, making sure that you still have the regular local ring or whatever it is, and then kind of apply inductive hypothesis. So that is the crux of the matter, and with some bit of technicalities here and there, which you can see. Okay, now how this is useful is, yeah, so a quick corollary. I told you that dimension 1 case will be the interesting one. So first of all, in case you are, I don't know, I mean, like it's not possible to discuss everything. So this is just, I have put it under this purple color. This is again like if a kind of a prerequisite material, if I may call it, that this is the definition. This is not the definition of discrete valuation ring, but you can treat it as a definition that if one of these conditions, all their equivalent, holds, then it is a discrete valuation ring. So basically, it's a Noetherian local ring. The last one, look at the last one, that R is a Noetherian local ring and its maximal ideal is non-zero and principal. This is what is called a discrete valuation ring. Keep this in mind. If you know this, good enough. If you do not, then please learn this, or else we can maybe have a quick round of discussion, or we can treat it as an exercise, okay? So I'll be using this, basically, this as a definition of discrete valuation ring more than anything else. So the corollary is a Noetherian local ring of dimension 1 is regular local if and only if it's a discrete valuation ring. Of course, it follows trivially, right? I mean, because dimension is 1 means you know what it is, okay? And suppose dimension 1 and regular local, then you know what it is, that it's an integral domain, maximal ideal is a non-zero and principal. Therefore, you use this and you have discrete valuation. And the converse, how about the converse? Can somebody quickly tell me? So if R is a discrete valuation ring, then is it obviously regular local? Use this for discrete valuation.
Its maximal ideal is principal.
Yes. Therefore,
Then embedding dimension will be 1, but it's a one-dimensional.
okay, fine. Okay. So therefore, the one important theorem has been discussed. You know, a very important property. More will be discussed eventually. And you have also understood dimension 0 and dimension 1 completely. Okay, for regular local rings. Okay. Now, oh yes, this is also a couple of corollaries. These are again like. Essentially, you can tell me the proof immediately. Don't look at the proof, okay? So let R be a regular local ring, 0 not equal to T belonging to M. If R mod RT is regular local and T is not in M squared, then dimension of R mod RT is dimension of R minus 1. Do you see the speciality? What is new being told here? Or you tell me the proof, or the proof is written here, but what exactly? So T is not in M square, so you know actually, here it is. Where did I write that? Here it is. So you know that if you have a regular local ring of dimension D and T is non-zero in M, then T not in M square if and only if R mod RT is a regular local ring of dimension D minus 1. So exactly this is what, yes. So if you have this, right? So it follows from a previous corollary that, so basically you want to show that T does not belong to M square, right? And you know that R is regular local and T is not in M. So if this is regular local ring, but if we have already proved that it's an if and only if condition, that when do you have this? Okay, so it's an integral domain and T is not 0. And therefore, we have this. Are you sure about this fact? Are you sure about this fact? Where exactly is integral domain being used here?
Because 0 is the minimal prime ideal.
Yes. So once you have this, therefore you have this. Okay. So please understand, I mean, maybe I should highlight it. Okay. So you have this And therefore this, so what is the significance of this? Therefore, if anybody can tell me.
Because this dimension can drop
Exactly
at most by 1.
Yeah, right, exactly. So therefore it's exactly dimension dropping by 1, and therefore you have this, so you have this regular local ring, sorry about it. Oops, not this. Yeah, you have the regular local ring condition, and you have proved that this, and therefore here you are. This is a regular local ring, dimension is dropped by 1, and therefore you have T is not in M square. Okay, so once again looks a kind of a technical information, but extremely useful. Okay, so look at the next corollary, that if you have a part of the regular system of parameters of a regular local ring R, then T1, T2, Tr is a prime ideal of height R. So that's what we want to prove basically. Okay, so you want to show that if you have a part of a regular system of parameters, you take the sort of the first R elements, and then this is a prime ideal of height R. Okay, so for every I in between 0 and R, you have, this is a regular local ring, and it's an integral domain. Is that clear to you? For every I between 0 and R, you have this quotient ring is a regular local ring. Why is that true? You are given that this is a part of a regular system of parameters. What is that we are using here? Okay, let us assume it for the time being. So you therefore, this is a prime ideal. That's integral domain, and therefore it's a prime ideal. Thus we have the chain. You can see this chain of prime ideals leading up to this, where the inclusions are proper because of the minimality of the generators. You know that, right? So it's minimally generated by these things. So this shows that height must be greater than or equal to R. On the other hand, you have this ideal T generated, etc. Therefore this, and therefore the equality happens. So now again, let me go back. So how do you have this? Because say, otherwise I won't be able to say that it's an integral domain, right? How do you prove that this is a regular local ring for every 0, for every I between 0 and R?
Because they are part of system of parameters.
Okay, are we using any result here?
Yeah, we proved it. We proved it in this lecture only.
Exactly. So, yeah, I mean, that's a problem. I mean, on a board, you kind of get to see everything. So we have, in fact, started with it that once you have a part of a regular system of parameters, this is equivalent, that this is a regular local ring of dimension D minus R. Exactly, it drops by R, right, from the original dimension of the ring. So therefore, you have this, please don't forget, this is going to be a very, very important thing, that once you go modulo a part of a system of parameters, regular local ring condition remains intact and dimension drops exactly by the correct amount, correct number. Okay. Okay. Good. So we have this. So we have some basic but important facts, and we have seen that going modulo a part of a system of parameters, it really helps. Okay. And please remember this, that going modulo an element like this, T non-zero in M, but T is not in M square. That's actually, it's very good in the sense that it's just going modulo one element, dimension drops exactly by 1. And you just have to ensure that T is not in M square. That's the only thing. Okay. So this is very, very useful to remember. Okay. Okay. So now I have a longish theorem where kind of some statements are equivalent, but you will see that how these are being used. So you have a Noetherian local ring of dimension D. Then R is regular local. So all these conditions are equivalent, and you can take any one of these now for working whenever you have a regular local ring condition. So every minimal generating set of M is an R regular sequence. M is generated by an R regular sequence, that is condition 3. And for every choice of a k basis of m mod m square, the graded k algebra homomorphism, you know what this is. We have already discussed this, quickly defined it in my previous lecture. Mapping the variables to the given basis. Okay. So there are d of them, because you know that this is a regular local ring of dimension. I'm sorry, this is a d-dimensional Noetherian local ring. So if you map these variables to this basis, then this is an isomorphism. And fourth and fifth, it says that there exists a k basis of m mod m square, such that this map where variables are being mapped to the basis I have just quickly described as in 4. This is an isomorphism. So these 5 conditions are equivalent. This is something very, very important and very, very useful. We will see that. Okay. Okay. So let us start. I think I will open it in 2 windows now. No, sorry, not this. Yes, here it is. Okay, so I hope you can see this. So this is the theorem we are trying to prove. So 1 implies 2. So you have regular local ring of dimension d, and you want to show that every minimal generating set of M is an R regular sequence. Okay. So you kind of can understand what to do. It's because you have already seen that going modulo 1 element, if you carefully choose it, then you retain the regular local ring condition, etc. Okay, so we may assume that d is greater than or equal to 1. Why? What is wrong with d equal to 0? Please answer.
That is a field, so.
So there's exactly. Okay, so assume d is greater than or equal to 1, then if R is a regular local ring, and suppose T1, T2, Td is a minimal set of generators of M, okay, then this is a regular system of parameters of R, of course. So we show by induction on D, I told you, right? This is going to be the technique on D, that the sequence Td is an R regular sequence. Okay. So to begin with, so since R is an integral domain and T1 is non-zero, okay, so T1 is a non-zero divisor of R. So R is regular local, so you have integral domain, and therefore you have started it. Therefore, this is a regular local ring of dimension d mod d minus 1. Are you sure? Why is this true? T1 is a non-zero divisor. Are you sure about this fact? Which observation have we used here?
It is a system, part of system of parameters.
A part of
Even.
system. So that's exactly the standard argument every time. You have a non-zero divisor here. You have already used the integral domain condition, and therefore it's a part of a system of parameters. Therefore, you have a regular local ring dimension has dropped exactly by 1, and its maximal ideal is generated by this. That's obvious because you know. So by induction, this is regular, and therefore this is R regular, and therefore M is generated by. So you know, I mean, this there's a very kind of a, you can sort of see that there's a kind of a routine behavior in this argument, and this will continue, but of course with some intermittent technicalities here and there. Any questions here? No? Okay. Okay. So how about 2 implies 3? So given that every minimal generating set is an R regular sequence, M is generated by an R regular sequence, so nothing to do. So we prove now 4 implies 1. Okay. Fine. So you have this, that for every choice of k basis of m mod m square, if you look at this homomorphism, the graded k algebra homomorphism where xi is being mapped to basis elements, then this is an isomorphism. From this you prove that R is regular local. Okay, so now please look at this. So M is generated by an R regular sequence A1, A2, AR. If you know that, then this will be true. But how do we get this, by the way? Oh, sorry, I meant to write. I'm very sorry. This is 3 implies 1. Oh. I will prove 2 implies 4. Okay, sorry. Yeah, this is 3 implies 1. Sorry. Yeah, this 3 implies 1. This is, I'm sure it's kind of obvious. So I'm proving 3 implies 1, and then I will handle 4 with 2. Okay. So if you know that M is generated by a regular sequence, then R is regular local. That's kind of obvious, as you can see, that you have this inequality, that your embedding dimension is less than or equal to R, but then you have this, okay? And therefore, since you already have a regular sequence of length R, so therefore depth is at least R, and therefore you have the equality all through, showing that R is regular local. Okay, so therefore I have this portion. Now comes this 4. Now look at this. This requires a little preparation, which I have again put under purple, because this again we will take it up as a discussion material or exercise or whatever. I think better to discuss during the tutorial, but we'll put it as an exercise problem. Okay, so it follows from the following theorem, that if you have a sequence of elements A1, A2, AR in R, assume that A is the ideal generated by them, okay, and proper. Now consider the graded R mod A algebra homomorphism given by this xi going to AI bar, AI are these, okay, and this AI bar is in this, the image in A mod A square. Now if this sequence is R regular, then phi is an isomorphism, and conversely, if phi is an isomorphism and if you have this condition, okay, you have seen this condition when we were talking about the separated condition in my previous lecture. So then this sequences are regular. Okay. So if you use this, then it kind of follows that. So what do you want to show? You want to show that 2 implies 4, right? So every minimal generating set of M is an R regular sequence. Fine. So once you have minimal generating set, therefore you know you will have a basis, k basis of M mod M square, and then you do it for M mod M square, okay, and apply this, and then you will have 2 implies 4. So we will please treat this as E stroke T, give it a try. This particular theorem is what I am talking about, and then we will see that 2 implies 4, and also 5 implies 3. So 5, you know, the similar statement, that is, if there exists a k basis of M mod M square such that this map is an isomorphism, and 5 implies 3. Basically, if you remember, if you notice that it's an, let me see, yeah, you have this, if this you have an unregular sequence, then you have an isomorphism, and you have the converse also. So you use this theorem again, and then your 5 implies 3 follows. So I have just kept it sort of pending, that maybe here also I'll just put that mark, because this helps us remember. And this one. So this is the key result, which will be used for proving both 2 implies 4 and the 5 implies 3. Okay. So what does this isomorphism mean? That if you have an isomorphism and the separated condition, then the sequence is M regular, R regular. But you know you are in a Noetherian local ring, and so you are using it for M mod M square. So you need this separated condition which is there, and therefore, okay. Okay. So now this theorem is going to be used in the following way. Let me show you how. Just, yeah, here you are. Maybe I keep this open. So here comes another structured theorem, so to say, that a regular local ring is Cohen-Macaulay. In fact, every regular system of parameters is a regular sequence of R. Okay. Now I have said that this follows from the previous theorem. Can somebody quickly tell me how? It's obvious, but still I want to hear it from you. How do you have this depth equal to dimension? And every regular sequence of parameters is a regular sequence that you have already said that every minimal generating set is an irregular sequence, or regular sequence, I'm sorry. And is this obvious? Is this okay? I'm talking about this corollary.
Part 2 says it, no?
Sorry?
The part 2 of the previous term says that
Yeah. It says what? The part 2 says what?
the depth is greater than, like every minimal generating set is in R sequence. So depth becomes greater, it becomes the height of M, which is dimension of R.
Absolutely. And of course, every regular sequence of system of parameters is a regular sequence, right? Okay. I hope it is okay with others too. Okay, so let me move on now. Okay, I'll here, as you can see that I have just said that we know that and it is easy to prove that, but of course I have not discussed it. Professor Patil will be talking about completions in detail, and we have already just said what is a completion, what is an emedic topology, to be very precise, nothing beyond. So I just sort of mentioned it. You will learn a proof, and after Professor Patil does, then maybe we can again come back to it. Okay. Okay. So so you have this fact, but do remember that that if you have the emedic completion of R, then R is regular local if and only if R cap is regular local. Once again, like you will see that in various places, you will see that let us assume that R is complete. Okay, so this is the reason. I mean, whenever you have at least the regular local condition, then completion actually does not change the scenario. It is in fact equivalent as long as you are having an emedic completion, and therefore you may sometimes assume that it's a complete regular local ring. Okay, but anyway, so these facts I have just sort of I have only mentioned, nothing beyond that. Okay, now. Yeah, so this I will not get into right now. This can wait for a while. I'll come back to it. Let me go back to the this thing. Let me go back to this flatness now, because I have the very basic stuff of regular local rings, and I have seen how to use system of parameters. I have seen what are the kind of standard inductive process. So let me now go back to this flatness thing. Okay. And I would like to keep certain parts open. For example, here, give me a minute, please. Yeah, let me keep this open. Yeah, let me keep this open. Okay, so now I'm back to this theorem. So if you remember, this is what we were discussing: Noetherian local rings, local homomorphism. You know what this is, and this is the fiber ring. And by the way, this is just a quick observation, as I have already said that this will be a part of the tutorial. and here you are. So this is the theorem. So R dash and F are as above. If R is regular local and R dash is Cohen-Macaulay, and if you have this dimension inequality, dimension of R dash is dimension of R plus dimension of F, then R dash is flat over R. Very, very useful one. Okay, and as expected, this proof is by induction on R. Okay, please make a note of this. Okay. Okay, so if dimension R is 0, please remember that R is regular local. Fine. Okay, so then of course it's a field and we are done. Now, dimension R positive. Take an X in M mod M square. Well, this is, I told you, right? This is going to be the process. Okay, you choose an element X non-zero and X in not in M square, and then set R bar equal to R mod XR. R dash bar is R dash mod XR dash. Then you have this dimension inequality. You have seen this a number of times, I'm sure. Okay, that you have this dimension dropping. It's the inequality is less than or equal to dimension of R bar plus dimension of F. Are you sure about this part? Are you sure about this part? The first inequality. Can someone respond? Why is this true? R dash is this. R dash bar is this. Okay. How do you have this? Where is it coming from? You don't forget that you have this condition. So is it clear to you? Because this is important, otherwise we won't have it. I have this, and then I'm going modulo X. Fine? Okay, if you assume, then what happens? Your dimension of R dash bar is less than or equal to this. Now, using a system of parameters of R dash bar, we see that this is greater than or equal to dimension of R dash minus 1. Once again, so what does exactly mean? Using a system of parameters, and therefore you have the equality. Okay, dimension of R dash is equal to this, and now it is not difficult to guess what is going to happen. But the main parts are here, that once you have gone modulo this X, which is in M but not in M square, now here you have this inequality, and here I have this inequality, that this is greater than or equal to also dimension of R dash minus 1. So what exactly is being used here? I'll put it. This is the first place.
The first place we are getting due to induction, because dimension of R dash bar is dimension of R bar plus dimension of F bar. And dimension of F bar is less than equal to dimension of F. So we are getting that.
F bar. What are you saying?
I'm saying that by induction we are getting, after going modulo X,
You
we
mean
are getting that
inequality? You mean this one?
first one.
Yeah, yeah.
Yes.
Okay.
So by
Yeah.
induction we are getting dimension of R dash bar is dimension of R bar plus dimension of F bar.
Yes.
And that is less than equal to, then dimension of F bar is less than equal to dimension of F.
Okay. Okay.
So first we are getting.
Second one. You always have that.
Second, it's like using like dimension can drop at most by 1.
Yes. Okay. Very good. So therefore, clubbing these two together, you have exact equality that dimension of R dash bar has dropped by 1. And then you know it follows that X is R dash regular and R dash bar is Cohen-Macaulay. How does it follow? If your dimension has dropped exactly by 1 and you started with an element x in m minus m square. Now, how does it follow that x is r dash regular and this is Cohen-Macaulay? What is that we are using here?
Dimension drops exactly by 1 depend only if x is a non-zero divisor.
Absolutely. Okay. So therefore, you have the correct, the depth dimension inequality is being preserved, and therefore you have the Cohen-Macaulay. Now you have induction because you wanted regular local ring, R should be regular local and R dash should be Cohen-Macaulay. So you wanted to make sure that both the things are true after you go by bar, right? So you have that. Therefore, you have R dash bar is flat over R bar. Now you have the Tor condition that therefore this is 0. Now, moreover, x is both R regular and R dash regular. Now, this is another thing which I don't exactly remember whether we discussed in this very format. So let me just underline it. Moreover, x is both R regular and R dash regular, which gives the tors are the same. Now, this is what we need, that when we want to take out the bar and come back to this original one, right? And therefore, we have the vanishing condition on this and vanishing condition on this would follow, and therefore R dash will be flat over R. So this one is what one needs, right? So I'm putting it under E stroke T because just to make sure that, so here, this regularity, x is both R regular and R dash regular, and because of which we have that. I mean, Joydeep, was it put as a tutorial problem? I'm not able to recall exactly. Is Joydeep around?
Yes, sir.
Yeah, was it put as a tutorial problem? This part?
E stroke T part.
Yeah. This moreover x is both R regular and R dash regular. Then you have the equality of the tors.
Yes, sir.
Yeah, I mean, so in one of these, maybe we would come back to it once again. I am not able to exactly recall that. So if you have this, then of course the proof follows. Okay. So now here you just let me just point out these places. So the very standard argument of first choosing this, then you have go modulo this, then you have the dimension inequalities and the induction. For induction to work, you need to show that your element is so chosen that you have the exact equality of this dimension, and also because of the R dash regular condition, and since you have gone modulo that, you have the Cohen-Macaulay ring condition as well. Induction has worked, and therefore you have the Tor condition. But now coming from here and to this, taking the bar off, you need this equality. This is what exactly, once again, we need to make sure. And therefore, this gives us that Tor 1 is 0, and therefore R dash is flat over R. Okay, so now this is a very important result. Now this theorem is what I don't want to get into right now. Okay, so that how the associated primes behave when you have a homomorphism of Noetherian rings, and if you have the flatness over R, then how the associated primes behave under these maps is what this theorem is all about. I'm not getting into this because I don't really have to use it for the time being, but I just thought that let me mention this. But I am coming to a more important thing right now. Okay, so is this clear to all of you, this theorem?
Yes.
Okay. Okay, so I mean, basically this, whatever we have discussed so far for the techniques, standard techniques for regular local rings, that going modulo a part of a system of parameters is what is being used here. And then the inequalities involving the dimension. That's it. I mean, these are the two things. You get used to it and then you will see that these things follow. Okay, so now, yeah. Yeah, so you have Noetherian local rings and a local homomorphism, and if M is a finite R module and N is a finite R dash module, if N is flat over R, then you have this equality of the depth, that the depth of this as an R dash module, you know, N is R dash module, so you have this R dash module structure for this. Then this actually adds up, but depth of M plus depth of N mod Mn over R dash. Okay, so this is very, very useful, very, very useful. You will see it a little later. That so let us prove this first. Okay, so please remember, I have Noetherian local rings and local homomorphism, and if I have a finitely generated modules M and N, and if I have the flat condition, this is very, very important, of course. Okay, then I have this addition formula for the depths for the tensor product on the left hand side, and then you have the steps on the right hand side. Okay, so let us start with the maximal M sequence and the maximal N mod Mn sequence. Okay, so y1, x1, x2, xr in M and y1, y2, ys in N. Remember, these depths are with respect to R and R dash respectively. Okay, and we are using, let me be a little careful. Yes, okay, so we will use this dash for the images in R dash, okay, under this map. So xi dash is the image of xi in R dash. Now, our claim is that this x1 dash to xr dash, that means inside N now, it's a local homomorphism, so they are in N now, and y1, y2, ys, these are plus s elements. This is going to be a maximal M tensor N sequence. So this is the main one, right? Okay. Okay. So how do you go about it? Any guess? How do you think we can do it? And where exactly the flatness is going to come into play? I mean, that will not be very difficult to guess, because you can understand that you will have a non-zero divisor and you will have a regular element, and then you will take the multiplication by that element and then you will use that. But point is, I mean, what kind of, are we going to use some kind of, and it's probably kind of gives you an idea that I have gone modulo some elements x1, x2, xr, right? So any guess what we can perhaps do? Okay, let us see. Okay, so here you are. This is our in M tensor N, and let us denote this by MR. Okay, so this is a summation. This should be I equal to 1 to R xim, M mod xim. Okay, then let me, yeah. Okay. I'm claiming that this M is an associated prime for MR, and this M tensor N modulo this xi dash M tensor N, this is this. So first of all, why is this true? x1, x2, xr to begin with is a maximal M sequence in M. Remember that, okay? And y1, y2, ys, you know what this is, a maximal N mod Mn sequence. So why is this true? Someone? MR is, you have gone modulo this submodule. Why is M in the associated prime?
Because this will be contained in the zero divisors. This is the maximal regular sequence.
Correct. Correct. Okay, and look at this. Can somebody tell me how one could possibly go about it? How does one prove this? Xi dash is the image of Xi in R dash. Let me again put it under a mark. How to prove this? How to distribute this part? How to distribute this part over here? I mean, what kind of map you would choose? What is the canonical way of doing it? What is the canonical way of doing it?
We have to take the map from M tensor n to MR tensor n. X comma y, sorry, X tensor y goes to X bar tensor y.
Suppose I admit that. So is this going to be a part of the kernel?
Define a map from M cross N to MR tensor N.
Absolutely. That is the first step. Next.
Then we will get a map from like M tensor N to MR tensor N. And then we try to show. Then we are trying to show that this is in the kernel. The quotient is in the.
Will you show that it is actually equal to the kernel? But so this is a part of the kernel is still okay. But will you actually show that any element in the kernel would actually belong to this? Where exactly, I mean, your Xi, it's an M regular sequence will come into play. So that's exactly where my question is. Okay. So so please, this is very, very important. I mean, it's not difficult or anything, but don't ignore this. Putting it this will be part of the exercise set again. Okay. Okay. So if you, for the time being, let us assume this. If you assume this, then it follows that y1 is n regular and n1, again, you can see the trick that going by just one less, sort of pushing it down by one element, modulo one element. Now, this is flat over R. I mean, again, why is this true? Why is this true? After that, you will see what is happening. But y1, so remember, your y1 is, oops, this is your y1, right? This is a maximal n mod mn sequence. From that, I'm trying to say that it follows that y1 is n regular and n1 mod this is flat over R. What is that if we are using here? What is the speciality of y1 which makes it happen? It was n mod mn regular, right? Part of that n mod mn regular. How can we suddenly say that y1 is n regular? Because if that is the case, then you have this, okay? And you have this. Just a minute. Yeah. Yeah, you have the flatness. Yeah, anyway, I'm coming to this later. So little later. So what about this? How do you show that y1 is n regular? how do we take the quotienting off? And if we assume that y1 is n-regular, then does it follow that this will be flat? Assuming we are given that n is, we are given that n is flat over R. Okay. So if you go modulo this submodule where y1 is n-regular, does it follow that it is flat? Do you remember any result that we have proved? No? Okay, so let me take you there. Yeah. So you see, this is what we will be using, okay, essentially, that whenever you have X sequence, if you have an M sequence, and if you go modulo this, now you can understand what was the purpose behind that construction. Then this is also flat, assuming that you have, just let me take you to the main theorem first. Yeah, here you are. So we showed that if you have Noetherian local rings with local homomorphism, and if you have a morphism of finite R dash modules, then N is flat over R. With this assumption, the following two are equivalent, that U is injective and N mod UM is flat over R, and U bar is injective. Now this is something which is extremely important, because this, now you will see it's being used again and again. And from this, we could write this corollary that if you have Noetherian local rings with local homomorphism, M is a finite R dash module. And if you have R dash bar, this, and for x1, x2, xn in N, if we write this as the images, then the following are equivalent, that this is an M sequence and Mn is this flat over R. If and only if this is an M tensor K sequence and M is flat over R. So this is what will be used again and again. So let me see if I can open this file here. So just a minute. Yeah. Yes. Yes, here you are. Okay, so this is what we will be using, and let me go to the next page. Yeah. Now can you answer? I have this. Yeah, here you are. And its corollary. The question is precisely this. N-regular, Y1 is N-regular, and this is flat. N is flat, that we know. And now, once you are done with this, then what you do is, proceeding similarly, we get this y1, y2, ys in MR tensor n. This will be an MR tensor n sequence, because this is, you know what to do. You go modulo x1, x2, xr, okay? Because see, okay, please remember this. Your x1, x2, xr, is an M sequence and Y1, Y2, Ys is an N mod Mn sequence. Now, here you want to prove that this is a maximal M tensor N sequence, right? So you are going one after the other. So basically, this is an M tensor N sequence. I don't know what is happening. Yeah. So this is an M tensor N sequence. Okay. And this was my new submodule, this quotiented by this submodule. And here, what is proceeding similarly? What does that mean, this proceeding similarly? That means every time I am coming by one after the other, first by Y1, then by modulo Y1, and then use Y2 and so on. Okay, and you use the regularity condition. And therefore, this is an MR tensor N sequence. And then we now have to prove that this R dash module, this has depth 0. Okay, so assuming that you write this, then if you can show that this has depth 0, then you are done, because then all your x1 dash to xr dash and then y1 to ys, right? You have quotiented by them. So that means now proving that this is depth 0, now this is where you are. Your y1, y2, ys in n is a maximal n mod mn sequence, and this is a maximal M sequence. So you use the maximality here. So if you can prove that this belongs to this set of associated primes, then you are done. Now this is exactly where we will be using this theorem. I told you that for the time being, I'm just making a kind of a cursory mention of this, but this will be taken up by one of us, or someone, or in the tutorial or somewhere. But I didn't want to get into this. So let me use it for the time being, that if I can prove that this belongs to the associated prime of MR, you know why I have already claimed, and this belongs to the associated prime of this NS mod MNS, you know what this is. That means that you just go modulo Y1, Y2, Ys, the submodule generated by Y1 N plus Ysn. And therefore, now if you can show that, then I will use the previous theorem to show that this belongs to the set of associated primes of the tensor product, and therefore it follows. Okay, so now here I have a bunch of things to verify. So bunch of things to verify means one is this, then this. Even here, when I am saying that, let me point out. Okay, for the time being, I'm putting it under E stroke T, but it will be a part of one of the lectures itself, but not right now, because we are just using it for the time being for proving some other results. Okay, so therefore, assume this for the time being, this theorem, and we are using it here to prove this the depth condition, and what it gives is the following, which I need for another result. So the corollary says that if I have a local homomorphism of Noetherian rings, and if this is the fiber, if you have the flatness of R dash over R, then you have this equality, which is now obvious if we prove that previous one. Okay, and then you have this very useful stuff that R dash is Cohen-Macaulay if and only if R and F are both Cohen-Macaulay. Okay, so therefore, under a flat extension, you have the Cohen-Macaulay if and only if Cohen-Macaulay, provided your fiber ring is also Cohen-Macaulay. So this is the, I told you, right? I mean, like we have seen certain conditions under flat descent, but now if you want to see that some more conditions, just flatness condition is not enough to say that this property holds here if and only if property holds here. This sort of factors in that the same condition on the fiber has to be used. Now this proof is actually very easy from the previous one, that here basically you are using it for R and R dash, that for proving that depth equality, because you know what we have proved here. So you have this depth equality. So you just take R and R dash as M and N. And therefore you automatically have the flatness because I'm assuming a flat homomorphism. Okay. And for part 2, you have this. So if R dash is Cohen-Macaulay, then obviously this will show you that you have 0 here. And therefore, since both these are non-negative and therefore you have 0 for each one of these, this will prove this. And similarly, for proving that these are Cohen-Macaulay implies R dash is Cohen-Macaulay, you just go back. Okay. So this is what so what we have done therefore is modulo this theorem and these verifications. Okay, so now I would like to again come back to it before I proceed further. So here again, can somebody tell me why is y1 n regular and n1 is flat? Can you tell me now? Yes, someone? Yes, Sampath?
I'm not sure actually.
Okay. Does this help you some way? The slide on the left-hand side. Okay, so I'm just postponing for the time being. Okay, it is actually here. Yeah, let me keep it. Yeah, this I will not get into. Professor Jacobi will have a discussion on this. So this is just a kind of, it will appear a little later that the flatness actually along with the fiber condition, along with conditions on the fiber, you have almost all the good properties they carry over under a flat extension. Okay, so the Gorenstein property can wait for some time. Instead, I will just again go back to, yeah. Yeah, just a quick introduction. Actually, Professor Patil will probably talk about it in detail. But right now, again, I need some basics for talking about this differential criteria for regularity. Okay, we will do this back and forth, that we will come back to regular local rings, and sometime later or at a suitable time, we will again go back to flatness. There's some important things like safe conditions and all to be talked about. Okay, so let me just quickly give you a few things and then stop. Okay, so we are trying to define the derivations. So this is the setup for us, that you have R dash is an R algebra and M is an R dash module. I'm mostly following again Matsumura and Professor Balwant Singh's book. So this map D from R dash to M is called a derivation. There is an additive group homomorphism and it satisfies the Leibniz condition. Okay, so this is such maps are what are called derivations. And if I say a derivation of R dash, then we mean that M is R dash and D is a derivation from R dash to R dash. Okay. Okay. Now these are some very simple facts which follow if you just use this. Remember, this is an additive group homomorphism and satisfies the Leibniz condition. So these are the two things that are the defining conditions for a derivation. Then you can prove that how derivation acts on a power, then d of 1 is 0. These things follow very easily. So I put them under green and under stroke T. Take this as simple exercises and verify them. And here you have that for any R elements in R dash and non-negative integers E1, E2, ER, you have this. Okay, how this is kind of a monomial in R dash. And then you can use a simple enough induction to prove this. Okay, now again some basic facts, that if you have a derivation and if you have, so the picture is something like, so you have from S to R dash and from R dash to M and then to N. Okay, so you have, this is phi, this is a derivation, and if you have any R dash linear map, this is a derivation. This is a ring homomorphism. Then this gives you a derivation. So these checkings are kind of simple. They are not difficult. Okay, so please do it. I just listed them down. And this is something very important, that if you have a derivation here, then you can prove that kernel, that means taking elements to 0, is a subring. And D is R linear. Remember, R dash is an R algebra. So R linear, if and only if this R dot 1, you know what it is, just the submodule generated by one cyclic submodule over R. This is contained in kernel. And in this case, you say that, D is an R derivation. Okay, and every derivation is a Z derivation. Okay, so these are certain, and then I will have a little more before I talk about, but today I think I have run out of time. I don't want to extend it. So we will see that we will be able to give two very important criteria for regularity. One is using the differentials, the regularity, the derivation, and the Keller differentials also I'll define, the module of Keller differentials. Using this, and another, we will come back to homological conditions again. Okay, so there's a very useful homological criteria for regularity. Okay, I think I'll stop here because certain things I have to wait. This will be developed in the next lecture, and then I will get into the criteria, and probably Professor Patil will have some more things which we will be able to use. So for example, completion and all, we are just making a cursory remark, nothing more than that, except just the basic definition of I-adic topology and all, which we have used in the previous lecture. Okay, so I think I'll stop here. Do you have any questions or comments? So please remember that this part is, there are quite a few things which have to be discussed. So this one definitely, this has been deliberately left out, and these verifications will follow from what we have done for flatness. Okay, so they have to be completed. Okay, so all these small parts have to be added, and then that makes it a complete proof. Okay, I think I'll stop sharing, and I will stop